first let's look at question 1. With question 1, the best thing to do is to draw the alcohols, but in skeletal formula. And the question is, which alcohol can be oxidized by acidified potassium dichromate? Now, immediately we know we can eliminate tertiary alcohols because they cannot be oxidized. So once we draw the structures out, we can see that 2,3-dimethyl-butan-2-ol is a tertiary alcohol, and so is 2-methyl-propan-2-ol. So they can't be oxidized, so we can eliminate those. Next, we can see that pentan-3-ol is a secondary alcohol, so that can be oxidized, and it can be dehydrated. How do we know if an alcohol can be dehydrated? Well, what you need is a next to or adjacent to the OH, you need another hydrogen. And you can see here that these have 2 hydrogens. The hydrogen and the OH could be eliminated and you'll get your alkene. However, with this alcohol here, which is a primary alcohol, it can be oxidized to an aldehyde because the H and the H would come off here to give an aldehyde, but it cannot be dehydrated because right next to it is a carbon, so you cannot remove 2 hydrogens to dehydrate it. So the answer to this one is B. Let's move to question 2. On question 2, immediately we know ethanol can be reacted with toluenes to form silver, so we know that that is correct. However, let's just look at the other possibilities. Does ethanol have a higher boiling point than ethanol? Well, we know that ethanol, by nature, all alcohols can hydrogen bond, and that means they've got much higher boiling points because they're strong against molecular forces, whereas all aldehydes can do is simple dipole, permanent dipole attractions. So that aldehydes always have a low boiling point. Its empirical and molecular formula are different. Well, let's write those out. Well, the simplest formula you can get is C2H4O, and you can't reduce that down to anything simpler, so that is also not correct. And the homologous series, if you look at the homologous series, the general formula of aldehydes, they are all C, so here that's C2H4. So therefore the general formula is CnH2nO. Let's now move to question 3. Which one cannot be produced by the oxidation of propan-1-ol? Well, let's go through all the possibilities, even though it's glaringly obvious that it's going to be propanone. So first of all, if we look at the complete combustion of an alcohol, you certainly do get carbon dioxide. If we look at the oxidation of propan-1-ol, here's propan-1-ol here. If we remove these 2 hydrogens with the oxygen, you're left with a single bonded oxygen, that double bonds up, and we form propanal, which is an aldehyde. So that one is produced. And finally, propanoic acid, well, aldehydes can be further oxidized to carboxylic acids. So the obvious answer to that one was B. Let's now move to question 4. Again, the best thing to do is to draw out the skeletal formula because it's the quickest way of doing it. So when you dehydrate propanol, you take off the OH here and the adjacent hydrogen, and you remove that, you eliminate it, and you get propene. And even if you flip that molecule around, you still get propene. If you dehydrate propan-2-ol, you could take off the OH here and this hydrogen, so you get propene, or you could take off the OH and that hydrogen, you still get propene. With pentan-1-ol, if you remove the OH there and the adjacent hydrogen, you can only get pent-1-ene. However, with pentan-2-ol, if you take off the OH and this hydrogen, you get pent-1-ene. Or if you take off the OH off here and this adjacent hydrogen, you get pent-2-ene. Question 5 is a typical easy percentage yield. And remember, on any percentage yield question, the first thing you need to do is to look at the balanced equation to get the ratio of reactants to products. So you can see here that propan 2O is being dehydrated to propene and water. And in here we're given the information, we're given the relative formula mass. So as usual, take down your essentials and put them into a table. So mass, MR, and therefore we know the amount, the number of moles, which is mass over formula mass. And we've been given the mass of the propan 2O and the mass of propene. We've also been given their MRs. So the most obvious thing to do therefore is to calculate the amount. Now because they react in a 1-to-1 ratio, the amount of propan 1O should be equal to the amount of propene obtained. And obviously because in any organic reaction there's other side reactions going on, there's amounts lost in purification, so you rarely get 100% yield, and you can see here that we haven't. So what you do is you write the equation, percentage yield equals actual moles over theoretical times by 100, and therefore the percentage yield is the actual moles of propene you obtained divided by the theoretical moles. That comes out to 85.736 figs. The answer's been given in 2, and the closest one is D, 86%. On question 5, we've got a reaction sequence. So what I've done is to number each of the steps. And this is a brilliant question for revising your reaction types. You can see here that the reaction 1, you have got, in step 1, you've got an alkane going to halogenoalkane. Now the only thing that will react with alkanes are free radicals. And because it's saturated, it has to be a substitution reaction. Step 2 is we are replacing the chlorine in the halogenoalkane with an OH. So it's definitely a substitution reaction, and we know that halogenoalkanes, because they've got an electron deficient carbon, are attacked by nucleophiles. So step 2 is nucleophilic substitution. Step 3, you can see the molecule has become dehydrated, it has lost water, it's an elimination reaction, and this is an alcohol. And alcohols undergo acid catalyzed dehydration. I've made a mistake here, that says base elimination. It really should say acid catalyzed dehydration. So my mistake there. Step 4, you're turning your alkene back into a halogenoalkane again. And alkenes, because they've got this electron-rich area here, are attacked by electrophiles. And because it's unsaturated, it's going to undergo addition. So that's electrophilic addition. So which one of those mechanisms isn't there? And you can see that electrophilic addition's there, electrophilic substitution definitely isn't there. So the answer to that one is B. Question 7, finally, again, is another nice reaction sequence, a fantastic way of revising your mechanism types. So if we look at step 1, you can see step 1 is an elimination reaction because we've turned a halogenoalkane into an alkene, and therefore we know that that is base elimination. Step 2, turning an alkene into a halogenoalkane, you've added across the double bond. This is an electron-rich region, so it's electrophilic addition. Step 3, you can see here, we're turning a halogenoalkane into an alcohol. You've substituted the Br for an OH, so it's a substitution reaction. And we know that nucleophiles attack halogenoalkanes, so it's nucleophilic substitution. Step 4, finally, we're turning our alcohol back to an alkene again. And what you've done here is you've eliminated, and when alcohols get eliminated, that's acid elimination. So, what do we need for each step? Step 1, base elimination, alcoholic KOH. Step 2, we're adding a hydrogen onto here and a Br onto there, so we need HBr. But with Br2, we would get a bromine going on here and a bromine going on here. So that is the wrong reagents. So the answer was B.